Hello, welcome to the course Excelling with Mathematical Modeling. Today we will discuss about some lake pollutant model. Now you must have noticed in which area you staying, if there is a lake, how dirty it gets. People throw things there, plastic bottles, plastic sheets and other dirts, and it gets polluted. So we take one such example where there are two neighboring lakes and how the pollution there is happening and what can we do about its control. So, let us take say two lakes A and B. So, the problem is defined like this, that you have an Vn. They are the total amount of pollutants in lake A and in lake B respectively after some year n. Now, every year 38% of the pollutant from lake A and 13% of the pollutant from lake B are removed. However, the pollutant that is removed from lake A is added to lake B due to the flow of water from lake A to lake B. And also it is assumed that 3 tons of pollutants are directly added to lake A and 9 tons of the pollutants are directly added to lake B. So, now you have to formulate a model on the base of this particular scenario. So, I have two lakes, lake A and lake B, and it says that 38% of the pollutant taken from lake A, 13% from lake B. However, this 38% it goes to lake B due to some flow of water. So, from lake B, if I take out 13%, which is 0.13, and from lake A, I am taking out 38%, 0.38, and it goes directly to lake B. So, that is the first part which has been told. Now, it is also assumed that 3 tons of pollutants is directly added to lake A. So, from here it is 3 tons and 9 tons to lake B. So, from here 9 tons. So, this is you can say some sort of schematic diagram which happens between lake A and lake B. So, you have UN, which is the total amount of pollutant in lake A, and Vn, which is the total amount of pollutant in lake B after year n. So, if I want to write the equation for UN, then I have to take into account the previous year's pollutant, then 0.38 of the pollutant goes out, but 3 tons are being added. So, that is our equation 1. When it comes to lake B, it is the pollutant from the previous year, then this 38% removed from lake A will go to lake B. So, plus 0.38 UN minus 1. Then 13% is removed from lake B, it does not come to lake A. So, it is minus 0.13 of Vn minus 1 and 9 tons are being added every year. So, 9 tons has been added. So, this two now gives the mathematical model of this pollutant in lake A and lake B, and let us look into their solutions. So, let me rewrite this. UN is equal to UN minus 1 minus 0.38 UN minus 1 plus 3, and Vn equal to Vn minus 1 plus 0.38 Un minus 1 minus 0.13 Vn minus 1 plus 9. So, once again this is the equation for lake A pollutants and this is the equation for lake B pollutants. So, in the lake A 38% is removed, 3 tons have been added, and in lake B this 38% comes to leg B. So, this has been added, 13% is removed. So, minus 0.13 and 9 tons has been added, and these are the pollutants from the previous year. Now, let us look into the equilibrium solution. So, by the definition of equilibrium solution, there will be no change from n minus 1 to n. So, no change from n minus 1 generation to n generation, and in such case you will substitute u n is equal to u n minus 1 equal to some u star and v n equal to some v n minus 1 equal to some v star. So, you substitute this in the original model and you will get u star is equal to u star minus 0.38 u star plus 3 and v star equal to v star plus 0.38 u star minus 0.13 v star plus 9. So, from this equation, this and this cancels and you get minus 0.38 u star plus 3 equal to 0, which gives u star is equal to 3 divided by 0.38, and this value will be approximately equal to 7.9. Now, from here v star cancels and you will get 0.13 v star equal to 0.38 u star plus 9. So, your v star is equal to 0.38 u star plus 9 divided by 0.13. From here u star is equal to 7.9. So, you substitute this value here and you get 0.38 into 7.9 plus 9 divided by 0.13, and this will give the value approximately equal to 92.3. So, I have the equilibrium solution as u star v star, where u star is 7.9 and v star is 92.3. Let us now look into the stability of this model. So, to find the stability, let me again rewrite the equation. It is u n is equal to u n minus 1 minus 0.38 u n minus 1 plus 3 tons and v n equal to v n minus 1 plus, this is added, 0.38 u n minus 1, 13% removed, v n minus 1 and 9 tons added. So, if I simplify them, I will get u n is equal to 0.62 u n minus 1 plus 3 and v n is equal to 0.38 u n minus 1 plus 0.87 v n minus 1, this and this, plus 9. So, the coefficient matrix A will be given by 0.62, 0, 0.38, 0.87. That is the coefficient of this. The coefficient of v n minus 1 is 0, coefficient of u n minus 1, coefficient of v n minus 1. Now, I have to find the eigenvalues, and for that it is A minus lambda I equal to 0, which will give me 0.32 minus lambda 0, 0.38, 0.87 minus lambda equal to 0. And this will give me lambda minus 0.62 into lambda minus 0.87 minus 0 equal to 0. So, from here it can be easily seen that lambda 1 is 0.62 and lambda 2 is 0.67. the two values of lambda, which we name as lambda 1 and lambda 2. If you now take the modulus, which is less than 1, take the modulus, which is less than 1, and you can say the system is stable about the equilibrium point u star and v star, which is equal to 7.9 and 92.3. So, this model which you have created according to the given problem is stable. We now check this numerically with the help of Microsoft Excel. So, we have this lake pollutant model, and so I put the value of n, value of un and value of vn. Initially, let us take the initial value is of the pollutant is 25. So, let me change the font size to 20, put some borders and make it in the middle. Okay. So, after simplification, the equation is un equal to 0.62 un minus 1 plus 3 and Vn equal to 0.38 un minus 1 plus 0.87 Vn minus 1 plus 9. This we have already seen while simplifying and checking for the stability. So, the first one is increase them by 1, which is equal to this cell plus 1, and then I drag it to the next 35 values. So, this number of values in your hand, you can choose them accordingly, and this value is equal to. So, I am calculating first this particular equation. So, if I put n equal to 1 here, this is 0.62 u0 plus 3. So, exactly that is what I am going to do. This is equal to 0.62 multiplied by u0, which I have taken to be 25 plus 3, and enter. This value is equal to 0.38 multiplied by un, which is un minus 1, rather u0, which is this, plus 0.87 multiplied by v0, which is this, plus 9. So, now I drag these two values to this much, then I highlight them pressing the shift and the arrow keys. So, I choose all these 34 values, 35 values, go to insert, go to scatter, and since it is a discrete case, I will choose this one, and I get a figure like this. So, as you can see that this is approaching the value 92.3 here, and this is approaching the value 7.9. Since the system is stable, so from whatever initial condition you start, they will reach the equilibrium point, and it is a local stability. Obviously, you can just change the series from here. You go to design, you go to select data, and here the series 1, edit, you write lake A pollutant, okay, go here, edit lake B pollutant. and you get. So, let us move back to the discussion. So, as we have proved analytically that your lake A pollutant will have the equilibrium value as 7.9 and the lake B will have the equilibrium value 92.3. So, as you can see, since the system is stable, they start from 25, which is the initial condition, and both of them are reaching their respective equilibrium values, which is 7.5 and 92.3 respectively. Let us now put some more clause in this particular model. So, as you know that the aim is that how to keep the lakes less pollutant. So, a team decided, okay, now our equilibrium solution should be 10 tons for lake A and 30 tons for lake B. So, how much of the pollutant now you can throw, or you can restrict that amount of pollutant for lake A and lake B to be thrown. So, which was previously the 3 tons and the 9 tons. So, now let us take them as x tons and y tons. So, you have the previous equation as un equal to 0.62 un minus 1 plus 3 tons and Vn is equal to 0.38 un minus 1 plus 0.87 Vn minus 1 plus 9. So, this was the previous model. Now, a committee has formed and they observed, and let us say they bring down the equilibrium solution to be 10 and 30, and for that you cannot throw 3 and 9 tons in the lake. Bring me the new values of x and y. So, now your equation will be un equal to 0.32 un minus 1 plus x and Vn is equal to 0.38 un minus 1 plus 0.87 Vn minus 1 plus y. So, what is known to you? You have known the equilibrium solution. So, you have un equal to un minus 1 equal to u star, that is given to be 10. So, your Vn is equal to Vn minus 1 equal to V star, and that value is given to be 30. So, we will be plugging this value here and solve for x and y. So, you will get u star is equal to 0.62 u star plus x. This will give x is equal to 0.38 u star, which is 0.38 multiplied by 10, and this is 3.8 tons. And V star is equal to 0.38 u star plus 0.87 V star plus y. So, your y is equal to 0.13 V star plus 0.38 u star. So, your V star is given to be 30, your u star is given to be 10, and this is minus, and this is 3.90 minus 3.80, which is 0.1 tons. So, y equal to 0.1 tons. So, basically now you are supposed to put 3.8 tons to lake A and 0.1 to lake B, so that your pollutants are less and they maintain the equilibrium solution of 10 and 30 tons respectively. We now look into the chemical pollution in a lake model. So, consider a lake, say area 2 kilometers square and average depth say 10 meter. It has a river flowing through it. So, if you consider this to be the lake and this is the river which is flowing through it, and say at a rate of 10,000 meter cube per day. Then there is a factory is built beside the river. This is the factory which releases 100 kg of chemical waste into the lake per day. So, what we want to find out is what will be the amount of chemical waste in the lake on succeeding days. So, you want to find out what will be the chemical waste in the lake in 30 days, 40 days, 1 month and so on. So, this is the lake and which has an area of 2 kilometers square. It has a depth of 10 meter. A river flows through it, flowing in and flowing out at a rate of 10,000 meter cube per day. There is a factory which deposits this 100 kg of chemical waste into this lake. We want to find out through a model that what will be the amount of this chemical waste in successive days. So, let us define the variables. Say WT, that is the chemical waste in the lake on day T, and T is the time measured in days. CT is the concentration of chemical waste. V is the volume of the lake. F is the daily flow of water through the lake, and R is the daily release of chemicals. So, with these variables, let us now formulate a model. So, the first thing we want is what is the lake volume, which is the area multiplied by the depth, and the area is 2 kilometers square multiplied by 10 meter. We have to convert it to meter. So, this is going to give 2 into 10 to the power 6 into m meter cube. So, 2 into 10 to the power 7 meter cube. So, that is the volume of the lake. Next is the flow through the lake or out of the lake. That is, the water is flowing in and going out. What is that flow? Denoted by F. Say this is denoted by V. So, that F is given to be 10,000 meter cube, which is 10 to the power 4 meter cube, and amount of chemical released in a day, we denote it by R, and it is 100 kg. Now, since the volume of the lake is fixed, the chemical concentration which is denoted by Ct is a known multiple of the total chemical waste, which is denoted by Wt in the lake. So, in kg per meter cube, the concentration is Ct, which is Wt per volume. That is Wt, the volume is fixed, 2 into 10 to the power 7. Now, for chemical waste, we look into the change in the amount of chemicals, which is given by Wt plus 1 minus Wt, and this will be equal to R if there is no river flow through it. But however, in this case there is a river flow, and hence some chemicals will be removed and flow downstream. So, the amount of chemical waste that leaves the lake each day is equal to the amount of water that leaves the lake that day multiplied by the concentration of chemical waste in the water. Now, this problem has a twist. It says that there is a river flowing through it, and because of that this waste, it won't remain constant. So, some chemical waste will leave the lake each day because of the flow, and hence the amount of chemical waste that leaves the lake each day is equal to the amount of water that leaves that lake multiplied by the concentration of the chemical waste in that water, which we have to calculate now. So, flow of chemicals out of the lake, that is equal to concentration Ct of chemicals in kg per meter cube multiplied by daily flow of water through lake in meter cube. So, this will be Ct, daily flow is F and the unit is kg. But you have shown that Wt is equal to V into Ct. So, basically this Ct we will be replacing by Wt by V. So, this is equal to Wt by V into F. So, F by V into Wt, which is the flow of chemicals out of the lake. So, therefore, change in chemicals per day, that is equal to amount added per day multiplied by amount removed per day. So, change is Wt plus 1 minus Wt, amount added is R and amount removed is F by V Wt. So, this is our model equation. So, let me rewrite it. Wt plus 1 minus Wt, which is equal to R, which is added. This is F by V Wt. So, this gives you the model of chemical pollutant in a lake where there is a flow of river. Now, to get the equilibrium solution, we assume there is no change in T and T plus 1 and we substitute that to be some W star. So, W star minus W star equal to R minus F by V W. This cancels and this gives W star equal to R V by F. And if you want to calculate numerically, you know the value of R is 100, the volume of the lake is 2 into 10 to the power 7 and the flow is 10 to the power 4. So, if you cancel all this is 10 cube 5, so it is 2, 1, 2, 3, 4, 5 kgs. So, this is the equilibrium solution of the chemical waste. Now, to find the stability, so let us write this function as, so you can write this as Wt plus 1 equal to Wt plus R minus F by V into Wt. So, let put Fw is equal to W plus R minus F by V W. So, F dash W, that is equal to 1 minus F by V. So, the system will be stable if mod 1 minus F by V, that is less than 1. So, you have everything fixed value, 1 minus F is 10 to the power 4, V is 2 into 10 to the power 7 and this value is 0.9995, which is less than 1 and hence the system is stable. And if you now want to solve this numerically, so I will substitute the values of R, F and V. and you will get Wt plus 1, that is equal to 1 minus F by V into Wt plus R. So, already you have calculated that your F is 10 to the power 4, your V is 2 into 10 to the power 7, and 1 minus F by V is gives 0.9995 Wt, and this is value is 100. So, let us see the solution of this model numerically. Say we want to find what will be the chemical waste after 10 days. Chemical waste after 10 days, taking the initial value is 0. So, at time t equal to 0, there is no waste. Let us now solve this equation using Microsoft Excel. So, I already have an Excel sheet opened here. The equation which I need is Wt plus 1, that is equal to 0.9995 into Wt plus 100. So, I just increase the font size. So, I need to solve this one with the initial condition that at time t equal to 0, the value is 0. So, let us first put this is equal to 0 plus 1, and let us drag it to say 10 days. And this is going to be, this is equal to 0.9995 multiplied by W0 plus 100. So, I just drag it to 10 days. So, you can see the waste after 10 days is 997.75. If you want to plot, highlight this to, go to insert, go to chart and click this. So, the chart title is growth of chemical waste. If you want to remove the grid lines, you click this. If you want to use axis title, you just click here. This is your time in days. And this is your chemical waste in kg. So, we now look into the analytical equation, and if you want to find the amount of chemical waste after 10 days from this particular equation, so all you have to put is T equal to 9. So, you can calculate what is W10 is equal to 0.9995 multiplied by W9 plus 100. So, basically you have to start with W1, W2 and go on calculating, and you will see that this W9 is coming to be 898.2 plus 100, and this is equal to 997.75, and this matches exactly with the numerical solution. So, with this we come to the end of this lecture where we have discussed the lake pollutant models. In my next lecture, we will be talking about the dynamics of alcohol model. So, this is one of the most interesting model. Till then, bye bye.